In the last lecture, we looked at complex reactions in a batch reactor. In this new topic, we will look at coupled material and energy balances in plug flow reactors. At the end of this lecture, you will be able to derive the model equations that describe the change in concentration and temperature along a plug flow reactor. And this could be coupled material and energy balances that have to be solved simultaneously. We will start with an exercise. And here we have a gas phase reaction that is carried out in an adiabatic plug flow reactor or a tubular reactor. The reactor has a diameter of 85 centimeters and a length of 1.5 meters. The reaction is A goes to B and C, and it is an exothermic reaction with a heat of reaction of negative 12.5 kilojoules per mole. Now, we are given a first-order rate expression for the reaction rate, and it is given in terms of the conversion of A. So here we have the rate of generation of A. K0 is the rate constant. Ca0 is the inlet concentration of A, and X is the conversion of A. We can also see that the rate expression depends on temperature. Since temperature is in the denominator, the higher the temperature, the slower the rate will be. The rate constant K0 is given by the standard Arrhenius expression, and this also depends on temperature. The Arrhenius constant, activation energy, and gas constant are given as follows. Here are more information about the system. We are provided the inlet temperature of 175 degrees Celsius, and the reactor pressure is assumed to be constant at 15 bar, and the inlet flow rate of A is 0.8 mole per second. We are also given the molar heat capacity of the mixture, which is in this case was assumed independent of composition and temperature. Therefore, it is uniform along the reactor. So what we need to do is to sketch the system and show the control volume, and then derive the model equations by writing the material and energy balances for the system. What we would like to find out is how the conversion and the temperature change along the length of the reactor. So that is X and T as functions of the position in the reactor Z. So we start off by drawing a diagram of the system. This is a tubular reactor, and we define coordinate Z along the axis and R in the radial direction. In the Z direction, we start off at Z equal to 0 and end up at Z equal to L. We draw our control volume as an element of volume with length delta Z. And this is because we would like to find out what the profiles of conversion or composition and temperature in this reactor are. So this is going to be a distributed model, not a lumped model. In the last lecture, we looked at batch reactors we took the control volume as the whole of the reactor because we assumed that everything is perfectly mixed and there was no dependence on position for any of the variables in the problem: concentration, temperature, and so on. Here, they are going to depend on the position inside the reactor. In principle, the radial as well as the axial position, but shortly, we will make some assumptions that will allow us to neglect the changes in the radial direction. Our control volume is a differential element inside the reactor. The next step is to write some assumptions, and the first assumption is it is plug flow. A plug flow reactor is an idealization and is the simplest type of tubular reactor. As you can remember, for plug flow to be true, we need a flat velocity profile along the radius of the reactor. The reason for this is if it is flat, then we don't have any axial mixing due to the different velocities at different radial positions in the reactor. So for example, if you have a fully developed flow and a quadratic velocity profile inside the reactor, the velocity of the fluid very close to the wall is very low, and touching the wall, we assume it is 0. And in the middle, you have the maximum velocity. So, at different radial positions, you have fluid flowing faster through the center of the reactor than it is through the wall. So you get mixing due to this effect. We do not want that for plug flow. Our assumption is flat velocity profile. The other thing we would like to assume is perfect mixing in the radial direction. So even though the fluid is flowing uniformly across the radius of the reactor, it is possible there's some mixing due to turbulence. We want to have mixing in the radial direction. If there's no mixing in the radial direction, for example, if we have an exothermic reaction, then the fluid close to the wall will be colder than the fluid on the inside. So there will be some energy flow from the inside to the outside, and you won't have a uniform distribution across the radius of the reactor. So if we have perfect mixing in the radial direction, everything is uniform temperature across the radius of the reactor. And finally, we want no mixing in the axial direction. In other words, no back mixing. So we want perfect mixing in the radial direction to make sure that everything is uniform across the radius, but we do not want any mixing in the axial direction, so no back mixing. All of these assumptions are needed for plug flow, and they allow us to draw our differential volume, which covers the whole radial cross-section of the reactor and small axial position, because we know that composition, temperature, and so on are going to change with axial position. Therefore, we will have a one-dimensional model. What we are going to do today is assume steady state. So we won't have to worry about the accumulation term. Chemical plants often run for long periods at steady state. So as a first approximation, we can look at just this scenario. However, in the later part of the module, we will consider the accumulation term. So it will be a dynamic distributed model instead of steady-state distributed model in this lecture. So in the future, the model will be in the form of partial differential equations instead of ordinary differential equations in this lecture. We will also assume ideal gas behavior, but you should know how to use the other equations of state from our first MATLAB tutorial if you cannot assume ideal gas behavior. We will also assume no molar expansion, which means that for a reaction that is not equimolar, for example, more moles of product than there are of reactants, or the other way around, there are more moles of reactant than there are of product. If that is the case, then you would expect the pressure to change in the reactor. Pressure might increase if you are producing more moles as the reaction is progressing, or it could decrease if you are consuming moles. Our reaction in this example is not equimolar, but we are going to assume equimolar to make life easy. So that means that the pressure in the reactor is constant, and therefore the density is also uniform. So the density will be equal to the inlet concentration of A, which is equal to P naught, the inlet pressure, divided by RT naught, which is the inlet temperature. Now we can start writing our model equations, and we will start with the material balance for component A. So again, here is a sketch of the system, and we add a bit more detail here. Here is our control volume at some position Z in the reactor, and the length of our control volume is delta Z. We have our inlet flow of A, and here is our inlet temperature. We have our outlet flow and temperature here. And then we need to know the flows in and out of the control volume. So we write down the axial heat flow, QZ, and the axial molar flow of component A, FAZ. So we have material and energy flows coming in at Z, and we have flows coming out at Z plus delta Z. So, to write our material balance, we go back to our fundamental balance equation, which is the rate of accumulation of A, that is, the volume times the change in concentration of A with respect to time, and that is equal to the A flowing into the control volume, which is FAZ, minus the A flowing out of the control volume, or the flow coming out of axial position Z plus delta Z. So that is FAZ plus delta Z. Now we have to write a generation term. The reaction rate is given in terms of the moles of A generated per m cube per second. So we need to multiply RA by the volume of the control volume. V is the volume of our control volume here. Now we can apply some of our assumptions. And the first assumption was that it was steady state. So this accumulation term disappears. So we have zero here. Our flow in and flow out are the same, and we can start adding in some information about the system for this generation term. So the volume V is the length of this control volume multiplied by the cross-sectional area of our reactor. So AC is the cross-sectional area. Delta Z is the length of the control volume. So this is our volume multiplied by the rate of generation of A. The next step is to divide each term by delta Z and take the limit as delta Z tends toward 0. And this will give us our first differential equation. So 0 equal minus the spatial derivative of the flow of A plus the cross-sectional area times the rate of generation of A. We've been given RA expressed in terms of the conversion of A. If you remember, the conversion X can be defined as the amount of A that has been reacted at any given point inside the reactor divided by what went in. So that is FA0 minus FA divided by FA0. So this X will be a number between 0 and 1. It may get to 1 at the end of the reactor, or it may not, depending on how long the reactor is or how efficient the reactor is. Because the rate expression is given in terms of X, it is also convenient to write our material balance in terms of X. We can do that by writing FA in terms of FA0 and the conversion. Then we will have a differential equation with just two independent variables, X and T. So we can rearrange this expression to get FA equal to FA0 times 1 minus X, which we can substitute in our differential equation and get this new differential equation. We then evaluate the derivative and algebraically manipulate the equation to get this. To recap, we have to write our material balance over our control volume in our plug flow reactor. The general material balance is given by accumulation equal to the incoming flows minus the outgoing flows plus the generation term. And we have to apply this over our control volume. So let's write out the expression for each term. The accumulation term can be written as the volume of the control volume times the change in concentration of A with time. The flows going into the control volume is given by FA. So I can write that down for the incoming terms, and this is evaluated at Z. The flows going out of the control volume is given by FA, evaluated at Z plus delta Z. The generation term can be expressed in terms of the rate of generation of A, for which we have been given an expression. So I have the rate of generation of A in terms of the moles of A per m cube per second. But I would like the unit of each term to be mole per second. So I need to multiply this by the volume of the control volume V. So we can drop this term because of our steady state assumption. So we'll have 0 equal to FA evaluated at Z minus FA evaluated at Z plus delta Z. And then I can express the volume of my control volume in terms of its dimension. So it's the length times the cross-sectional area. So I have delta Z times the cross-sectional area AC times RA. So now I can divide each term by delta Z. So it will become, so my equation will become 0 equal to FA at Z minus FA at Z plus delta Z. This is divided by delta Z plus AC RA. And then I can take the limits as delta Z tends to 0. So by definition, the limit of this term as delta Z tends to 0 is, okay, so this is the negative derivative of FA with respect to Z. And then I write down the rest of my terms here, ACRA. So we are given the rate expression RA in terms of conversion. RA is equal to negative K naught CA naught times 1 minus X all over 1 plus X times T0 over T. Okay, so since RA is given in terms of X, conversion X, it is convenient to write the whole material balance in terms of conversion X. So we know that by definition, the conversion X is equal to the amount of A that has reacted divided by what went in. So the amount that has reacted at any point Z is equal to FA0. So this is the amount at the inlet minus the amount at any given Z, FA, divided by what went in. So that's FA0. So we can rearrange this to, okay, so this will become FA0 times X equal to FA0 minus FA. And then we can solve this equation for FA. So we can write FA, okay, is equal to FA0 times 1 minus X. Okay, so now we can substitute the expression for FA in terms of X into this equation. Okay, so replace this with this. So we'll have 0 equal to, so negative derivative of FA, which is equal to this. So we'll have FA0, 1 minus X dz plus AC RA. And then evaluating the derivative, so I'll have 0 equal to negative dFA0 dz plus derivative of FA0 times X over dz plus AC RA. Okay, so FA0 is constant. So we can drop this term and we'll end up with, okay, so I can take FA0 out of the derivative because it's constant. So I can write FA0 dx dz plus AC RA. Okay, so now I can rearrange this equation to become, so I'll have FA0, and then I'll move the AC to this side. So I'll have AC dx dz. Okay, and this is equal to negative RA. Okay, so I'll move this to the other side, so it will have a negative here. Okay, and RA is given by this. Okay, so I can just substitute this expression to here. So I'll have, this is equal to K naught, CA naught, 1 minus x, 1 plus x, times T naught over T. So this is the expression that we just derived. So you can see that we cannot solve this material balance because we have temperature here, and K naught is also a function of temperature. So we need our energy balance to get an equation for the temperature. So for our energy balance, going back to the diagram of the system, this is the same as before. So now, for our energy balance, the flow in is QZ. Capital Q is heat flow. Small q is the heat flux. So this QZ is our heat flow into the control volume. And the heat flow out of the control volume is QZ plus delta Z. And so we write our balance equation as before. Our first term is accumulation, and that is equal to the flow in minus flow out plus the generation of energy. The accumulation term is the amount of energy in this control volume. The amount of energy per unit volume is the molar density times the molar heat capacity times the temperature. You should know this already. Q is equal to mc delta T. But this is not m. This is rho, the density. So we have to multiply this by the volume. And this is fixed volume. It is a cylindrical tube, and the volume doesn't change. We are taking a fixed volume so that V can come out of the derivative. This is our rate of accumulation of energy inside this control volume. The flow is QZ, and the flow out is QZ plus delta Z. And the energy generation term is the rate of reaction, which is minus the rate of generation of A. We have the minus sign here because we want a positive term, but we know that A is getting consumed. In other words, we only want to know how fast the reaction is going. The rate is per unit volume, so we need to multiply it by V. Then we multiply by the heat of reaction. We have a negative sign here because the heat of reaction is negative for exothermic reaction. And if it is an exothermic reaction, the energy in the system is going to increase. As the reaction proceeds, the reaction inputs energy into the system, and the temperature of the reactor is going to increase. That's why we have a negative sign here. Okay, again, we just want this whole term to be positive because it is an exothermic reaction. The sign and the units could be confusing, so always check them out. The next thing now is to write a formula for Q in terms of the variables in the system: temperature, pressure, and so on. We want to know what the heat flows in and out of the control volume will be. For heat flow, potential contributions could be from convection and conduction, or dispersion if you have turbulence. We already assumed plug flow. We said that there was no actual mixing, so that means our heat flow is only due to convection. So, if you remember how to write heat flow rate is equal to the heat flux, so that's lowercase q, times the cross-sectional area of the tubular reactor. So now, we need to write our expression for the heat flux, small q, in terms of the temperature. Temperature is what drives the heat flux. And for convection only, that is the fluid velocity times the energy density. So small q is equal to the fluid velocity V, the density ρ, the molar heat capacity Cp times the temperature. And then heat flow, the heat flow rate, is equal to the heat flux times the cross-sectional area AC. It would be nice to write this in terms of the inlet flow rate, FA0. And we can do this easily because we assumed that the density, so the rho here, is constant. If we assume that the velocity is constant, then we can write FA0, the inlet flow rate, equal to rho V times AC. And then we can substitute this into our differential equation. And we can get the equation at the bottom of the slide. To recap, we need to write our energy balance over the control volume. The general energy balance is accumulation equal to in minus out plus the generation term. The accumulation term is the change in energy inside the control volume. And we can write that as D times rho Cp T dt. Okay, so this is per unit volume, so we need to multiply this by the volume of the control volume V. The heat flow rate going into our control volume is Qz, or Q at Z. The heat flows coming out of the control volume is Q Z plus delta Z. And then we have the generation term. So the reaction is exothermic, so it is contributing energy to the system. So I would like that term to be positive. So I will write negative RA. So this is the rate of consumption of A, or negative the rate of generation of A. Okay? Multiplied by the heats of reaction. Okay, so again, I would like this term to be positive. That's why I have the two minus signs here. The rate of reaction is per unit volume, so we need to multiply this by V. Okay, so each term in the balance has the units of joules per mole. So you have to be careful because delta HR is given in kilojoule per mole. So you have to convert that first to joule per mole. Okay, so we can drop this term because of our steady state assumption. So we'll have 0 is equal to Q at Z minus Q at Z plus delta Z. And now, as we did in our material balance, we can define the volume of the control volume in terms of its dimension. So we have plus, okay, so delta Z, so the length of the control volume times the cross-sectional area. That would give us the volume of the control volume. Okay, so now we can divide each term with delta Z. So we'll have 0 Q Z minus Q Z plus delta Z. This is all over delta Z plus AC RA delta H R. And then I can take the limit as delta Z tends to 0. Okay, so by definition, this term here is negative dq dz. Okay, so definition of derivative. Plus AC RA delta HR. Okay, so now I need to write an expression for Q in terms of the system variables. Okay, so if you can remember, we can write the heat flow rate in terms of the heat flux, Q. Okay, so small q. So we have to multiply this by the cross-sectional area of the control volume. So heat flux can be due to, okay, so this can be due to conduction or convection. Or if you have turbulence, you can also have dispersion. Okay, so we already assumed plug flow. So therefore, we don't have any axial mixing. Okay, so we only have convection for plug flow. Okay, so now we need to define Q, small q, the heat flux for convection. So how do we do that? Okay, so if you can remember, so the heat flux is equal to the molar flux times Cp and temperature. Okay, so what is the molar flux? Okay, so molar flux, so I have the velocity, V, times the density. So that's the molar flux. To get the heat flux, I have to multiply this with the molar heat capacity and the temperature. Okay, so again, this term here, this is our molar flux. And this whole term here, that is our heat flux. So since the velocity, density, and the molar heat capacity are all constant, okay, then I can write the product of the density times velocity times the cross-sectional area as equal to our inlet flow rate, FA0. Okay? Again, because we assume that the density, velocity, and cross-sectional area are constant. So they are just equal to the inlet flow rate. So therefore, I can now write the heat flow rate, Q, okay, so this is equal to small q here, but I know that velocity times rho times AC. Okay, so let's write q first. So small q is V rho Cp times T, and then I have the AC. Okay, and then we will use this. So rho V times AC, that's just FA0. So this is just equal to FA0 times Cp T. Okay, so now I can substitute the expression for Q into our differential equation. Okay, so we will have, okay, so 0 is equal to negative D. Then Q is just this expression here. So FA0 Cp T. Okay, this is dz. Okay, plus AC RA delta H R. I can then evaluate this. So this will give me negative FA0 Cp dt dz. Okay, plus AC RA delta H R. And then I can rearrange FA0 all over AC times Cp dt dz. So this is equal to, okay, so I only have RA delta HR on this side. This is our energy balance. You can see that we cannot solve our energy balance either on its own because RA depends on X and T. Okay, it depends on the conversion and the temperature. And if you can remember our material balance, the dependent variables in the differential equation are also X and T. So we have to solve our material and energy balance simultaneously. That is what you're going to do in the MATLAB simulation session 3. What I would like you to do is to solve the coupled material and energy balance equations that we just derived and provide the plots of conversion and temperature as a function of the axial position in the reactor. The full problem sheet is now available on Moodle, so download that now and start working on it so that you will be prepared for our next session this week. To summarize, in this lecture, we learned how to derive the model equations for a plug flow reactor that describe how the conversion or composition and temperature change along the length of the reactor. We derived the model equations from the material and energy balances. The rate of generation of A was given as a function that depends on the conversion of A and the temperature. Therefore, it was most convenient to express the material balance in terms of conversion as well. Since the rate of generation of A appears in both the material balance and the energy balance, these two equations are coupled, and we have to solve them simultaneously.